Okay, good morning, every people. It's my pleasure to introduce Professor Fatih Temizsu from Bengal University. He will talk about summability methods, and this is one of our activity of our research group is to invite some professors from different universities and to teach introductory courses for undergraduate students. So we finish to give the word to Professor Temizsu. Enjoy with this course.
Thanks. Thank you. Okay. Did I do good? I'm not sure. Okay. So, is the sound okay to you? Is the sound great? Okay. Okay. Yeah. This will be my first time to give any course or speech through microphone, so I might look a little bit weird. So forgive me for this. Okay. So I am, as Professor Fernando said, I am Fatih Temizsu from Turkey. I have been researching on the topic of summability for the last 7 years. I'm so happy to be here. This will be my first time to ever give any course to foreigners. So this will be challenging to me as well. So first of all, I am so happy that you come here to listen to my presentation. It's an honor. I truly appreciate Professor Fernando's efforts letting me come here and signing some necessary papers. Without his help, I couldn't have done it here, honestly. So I am grateful to him and the whole university. The whole process was very fast. It didn't bother us at all. It was very fast, so that made me very happy. So, as you might be familiar before, today I will be talking about an introductory information about sequences and infinite series that you might be familiar before, some of the stuff that I'm gonna share with you. But I believe they play a very important role in the whole concept of summability and in particularly in statistical convergence of sequences. Okay, so I'm going to start with the elementary definition of a sequence of real numbers. I mean, generally speaking, range of any sequence, it can be any non-empty set, but we will be focusing on sequence of real numbers or complex numbers. I will be talking more on real number sequences, which is kind of a little bit easier to deal with. But many things that I'm gonna talk about today can be considered for complex number sequences as well. Sequence of numbers. Okay, so definition. We know that any function whose domain is natural numbers numbers, which we denote by this, is called to be sequence. Unlike the well-known notation, we don't use the notations F or G's for sequences. We use AN or AN runs from 1 to infinity, or XN for denoting sequences. So when if the range of the sequence AN is real numbers or complex numbers, we call them sequence of numbers. We mostly focus on this type of sequences. Let me remind you some very introductory concepts of sequences, which will be popular in our general concepts about summability methods. One of the most fundamental concept is convergence of a sequence. Convergence of a sequence of numbers. Let AK be any be a number, a sequence of real numbers, and L be in R. If for each positive epsilon there exists a natural number cap n in natural numbers such that n greater than cap n implies an minus L is less than epsilon. Then we say that the sequence AK, sorry, this is AN, I'm sorry. We say that the sequence AN converges to the number L, and we denote this by this. So this is the very most initial concept of sequence of numbers. I mean, all the time I'm gonna be expressing out that sequence of numbers, because these concepts can be generalized to other type of more general sequences. But mostly I will be talking about sequence of real numbers, so we will generally be using the usual metric of real numbers, which is absolute metrics. So another important concept is boundedness of a sequence. Boundedness of a sequence. If an is a sequence such that the following hold, then an is called bounded. There exists a positive m greater than 0 such that an less than or equal to m for each index n. Sometimes I might be calling these n's as indexes of sequences. So if we have this inequality for all indexes of an, then we call this sequence a bounded sequence. A very popular proposition between this concept can be summarized as follows. We know that if an is convergent, then it is bounded. But the converse of this does not hold generally. For example, it is very straightforward to verify that the sequence of -1 to the power n is bounded but not convergent. Yeah. Let me check my notes here. Okay, if for a sequence, if this definition does not hold, then we call it a divergent sequence. And we know some elementary results of convergent sequences. I don't want to give them in a very detailed way. I mean, for example, if we have two convergent sequences, then the subtraction or addition of these sequences are also convergent, and the limit is preserved by the addition of the limits of the aforementioned sequences. Yeah, another very important but introductory result is called sequence theorem. Some call it as well, call it also as a sandwich theorem, which is very popular among people who works on summability theory. Let me share it with you. Sequence theorem. Let AN, BN, and CN sequences such that AN is less than or equal to BN is less than or equal to CN for all n greater than cap m for some cap m from natural numbers holds if the limit of AN equals limit of CN with the limit cap L, then the sequence which is in the middle of AN and CN also convergent to the same number cap L. This is a pretty fundamental result, but it plays a very big role in many papers related to sequence spaces or summability concept, because we most of the time use this this fundamental result to prove some theorems. So we will be using it a lot. Okay. Okay, now I will be focusing on series, infinite series more, because we, thanks to them, we will be arriving at the concept of summabilities. To be talking about what a summability method really is, we will need to know about infinite series seriously. So I will be focusing on them more. Around 18th century, there was a very problematic issue among some well-known mathematicians. Some of them tried to deal with infinite series, but since they had complete and concrete definition of summation of an infinite series, they didn't want to deal with them after a certain point. And very well-known instant is of Abba's point of view. For a couple of series, they realized that an infinite series can be summed very different numbers. So he called them evils problems, evil series. So it does not make any sense to him to study on infinite series. Let me explain it to you. Infinite series. The problem is the problem starts with a very basic sequence. Honestly, let xn be given as n is odd 1 and n is even -1. We want to try to sum all of the terms of this sequence. So let me use this notation for the infinite summation of these sequences. This sequence, then we can write is like this. And it goes on like that. So one can manipulate this infinite summation like this. Then we can arrive at 0, right? If we manipulate it that way. But some other mathematician can come up with this cunning idea, which is very easily 1 plus then we would arrive at 1. We can even go further than this. Let me explain it to you. 1 minus s is equal to this infinite summation. So actually this is the same infinite summation that we used initially. So, but if we compute the summation by distributing minus in this summation, we would arrive the same one. So this is also s. So s would be 1 over 2. So because of this absurdity, some mathematicians back then called them evils problem for such series. They approached the issue to this way because they were not clear about the absolute definition of an infinite, the summability of an infinite series. So we need to give it clear definition, so that we can refrain us from such problems. I mean, it is so clear that we don't have such a problem with finite summations, finite series. If we have a finite number, many numbers, we can easily add them up. But when it comes to infinitely many numbers, we gotta be very careful on this issue. So let me give you the fundamental definition of a series. Let AN be a sequence of real numbers, the infinite sum of the terms of AN which is denoted by this notation, is called an infinite series. Yeah. So this is called an infinite series. We are interested in giving this infinite summation and meaning. What is this? What is the result of this? If we can give it a unique number, how or in what way one can do it. So we need another concept to give it a limit, a sum, which is called the sequence of partial sums of the series. The sequence whose general definition is the first summation of the first n summation of the series, which runs from 1 to n. K runs from 1 to n, is called the nth partial sum of AN, the series. This finite summation of the first n term of the sequence is called the nth partial sum of the series AN. So we are gonna call the series AN convergent if the sequence Sn, which is, as I said, the the sequence of partial sum of An converges. Okay. If limit n of Sn exists, finitely, then we say that the series An is convergent or summable to the number S, to S. So by this definition, we get rid of this absurdity, this nonsense, because if we easily compute the sequence of partial sums of this infinite series, we see that it is not convergent, because yeah, okay, I will arrive at this example later. Okay. So if the partial sum, the sequence of partial sums of series is divergent, then we say that the series is divergent. Okay. One of the very popular series is geometric series. I will just give them in a very brief way. Okay. An example. If the absolute value of A is less than 1, then the geometric series of A to the power n is convergent to 1 over 1 minus A. It is pretty easy to confirm that. One can easily confirm that partial sum of it is equal to 1 minus a to the power n plus 1 over 1 minus a. So I have not mentioned it, but we know that if a, the absolute value of a is less than 1, then the sequence an converges to 0. So thus the infinite series a to the power n is equal to 1 over 1 minus a, provided a is less than 1. Okay. So let's go back to the first series that we talked about. The series is divergent because its partial sum Sn is in that way. If n is odd, if n is even. So it is clear that this sequence is divergent. So this is the main problem that we had here. Because of this result, we can easily say that anyone can manipulate any series that way if he is not careful enough for the exact definition of summability of a series. So by this definition that I wrote here, we can refrain from this nonsense, and that way we don't have to call them Evil's problem. Okay. Very fundamental proposition can be mentioned as follows. A series A and with with positive terms converge if and only if its partial sums is bounded from above. Yeah, the proof is pretty easy. We know that because each term of this series is positive, the partial sums of this series has to be increasing. And also we said that if the partial sums is bounded from above, because of very well-known property of increasing sequences, we say that then this partial sum is converged to its its supremum. So if we say Sn equal to K1 runs 1 to n, then the limit of Sn is equal to supremum of Sn, since Sn is increasing and bounded from above. Okay. So this is the usual definition of convergence of a series. There will be in our further talks, there will be some series that are not convergent in usual sense, but that can be summed into a finite number with another type of convergences. One of the most well-known of these non-usual type is called Shizaro convergence of a series, which I will be talking now a little bit. Okay. Okay, Cesaro sum of series. Let A and B given. I mean, for convenience, sometimes I will be using this denotation for infinite series without repeating the n runs from 1 to infinity. We will take this as the infinite series of an. Be given the Cesaro sum of this series is defined by the limit of this average mean of the terms of partial sums of the series. As you may see here, the sequence is actually the average mean of the partial sums of the series. The first n term is divided by the number of the terms. So this is called the Cesaro sum of the series. If this limit exists, then we say that and the series A n is C or C1. Sometimes we just write C1, write C1. Cesaro summable is C1 summable to L provided that limit of 1 over n equals to L. So a very well-known example again can be reused from this example. As we said before, it is not convergent to any number because its partial sums does not form a convergent sequence, but we can easily give it a limit thanks to Cesaro sum of the series. Okay. Okay, for the series we easily find that the Cesaro sum of partial sum of the series is equal to 1 over 2 plus 1 over 2n if n is odd. And it is 1 over 2 if n is even. If n is even. So it is so clear that this sequence, which is the Cesaro sum of the original series, converges to 1 over 2. So then limit of Sk is equal is 1 over 2 as n tends to infinity. Thus the limit J1 an equals, sorry, is equals to 1 over 2. So as you see here, even though the original series does not converge to any number with usual sense, we are able to give it a limit with another type of convergence. We will be using these approaches a lot in our coming talks. Actually, this is where we arrive at summability methods. We most of the time try to give some non-convergent sequences with usual senses, give them new type of limits with different ideas. That's where we arrive at summability methods. Okay. So now I'll be talking about the Cauchy condition for series, which might be very important for some cases of series. The Cauchy condition. Okay. So, theorem, Cauchy condition. The series AN converged if and only if for each positive epsilon, there exists cap n in natural numbers such that this finite summation less than epsilon for all such that holds for all n greater cap n. So what is the importance of this condition? Most of the time it might be challenging to find the exact limit of series within usual sense or non-usual sense. But nevertheless, we are interested in finding whether or not it is convergent. So as you can see here, we don't use any limit of real numbers. We did not write the exact summation, the exact result of this series. We are just interested in if it is summable or not. I mean, the exact view is used also for the notion of cosinus of sequence, as you can remember. I mean, even though we sometimes we don't know what is the limit of convergent sequence with a traditional way, but we can use the cosinus of a sequence. I mean, the difference of the terms of sequence can give us an idea if it is convergent or not. The same thing comes here as well. I mean, as you can see, we just use finite part of the whole series here. It's runs from a specific index to n, such that greater than a specific number n, if for each epsilon we have a specific cap n dependent on epsilon, then we say that this series is convergent. Let me give you the proof of it, which is pretty easily understandable. Proof. I mean, these proofs might look very too fundamental for you, but honestly, in some of very difficult proofs of the current results that we are dealing, we most of the time use these fundamental methods, right? So to me, it is important to take a look at them. So we know that the series converges if and only if the partial sums, the sequence of partial sums is Cauchy, right? I mean, since here we are dealing with the sequences of real numbers, we can use the concept of being a Cauchy sequence. I mean, we know that real numbers form complete metric space. So because of it, being a Cauchy sequence and being a convergent sequence is exactly the same. So we can say that any infinite series of real numbers is convergent if and only if the sequence of its partial sums is Cauchy sequence. And if Sn is a Cauchy sequence, then it is convergent. So because of this, the series is convergent. Then we can use the fundamental definition of being a Cauchy sequence here. So then I wrote there is Cauchy. So what does it mean? This means that for each epsilon positive, there exists positive natural number which is dependent on epsilon exists such that the difference of Sn and Sm, which is actually this finite sum. I mean, since n is greater than n, we can write this. We can have this result from this subtraction. Would be less than epsilon for all n greater n. So this is exactly what we would like to arrive at. This proves the claim. So thanks to this Cauchy condition, we can prove very basic, one of the very basic results of convergent series. If the series an is convergent, then the limit of an has to be 0. So if the series converges, if the series converges, then it is Cauchy, right? It is Cauchy. I mean, it holds the Cauchy condition. So taking m as n minus 1 in the Cauchy condition, we find that for every epsilon positive, there exists cap n from natural numbers such that equals exactly AK less than epsilon for all n greater than cap n, which is actually the definition of convergent sequence. This means that the limit of an is equal to 0. So this basic result is very crucial for many cases, because if we need to deal with convergence or especially non-convergence of infinite series, we most of the time use this theorem firstly. Yeah. For example, let's go back to the geometric series. Example, yeah. I mean, if the absolute value of A is greater or equal to 1, then we know that the limit of an is not 0, right? Thus the infinite series of A and the geometric series of A n is divergent if the absolute value of A is greater or equal than 1, because the sequence is not null sequence, does not converge to 0. So because of this theorem, because of the converse of this theorem, we can deduct that then the series cannot converge because its general term is not a null sequence. But we gotta be very careful using this theorem, because just because the term of infinite series converge to 0 does not mean the whole series is summable. For example, the harmonic series even though we know that the sequence of 1 over n is a null sequence. The harmonic series of 1 over n does not converge. So what we benefit from this theorem mostly is when making sure that a series is not convergent. If we know that the general term of the series, which is an, is not a null sequence, then we can easily say that the series is not convergent. So another important concept is called absolutely convergent series. That will be playing a crucial role in our further courses as well. Absolutely convergent series. We say that the series an is absolutely convergent if the infinite series of absolute value of the terms forms a convergent series. If is convergent. Yes. If an is convergent but not absolutely, then it is called conditionally convergent series. Convergent. So we will be proving that every absolutely convergent series is also convergent, but before doing that, we will be given a couple of examples of absolutely convergent series. Okay. The geometric series AN is absolutely convergent if AN is less than 1. I mean, it is pretty easy because the term of geometric series are positives, so it is exactly equivalent to absolute convergence of the series. But a more interesting example might be given from harmonic series. Example. The alternating harmonic series, which is not absolutely convergent, because we just showed that we just told that the harmonic series is not convergent, and this is the alternating version of harmonic series. So if we use the absolute value in the general term of the sequence, we will get the usual harmonic series, which is not convergent. So because of this, we say that this alternating harmonic series is not absolutely convergent. So to be able to prove the theorem that says every absolutely convergent series is also convergent, we will need to define what a positive part and a negative part of a real number is. Definition. The positive part of the positive and negative parts of a real number A from real numbers are given by as 0 and if A is positive, it is 0. It is absolute value of A if else. So these two number is called the positive part and negative part of the real number A respectively. As you can see, if A is a positive number, then its positive part is defined to be itself, and if it's not positive, then it's defined to be 0. And the negative part of 0, A, is defined to be 0 if it's a non-negative number. If it is non-negative, if it is negative, then it is defined to be its absolute value. So one can easily confirm that the following equalities and inequalities hold thanks to these definitions. It follows that 0 is less than or equal to positive part of A, and negative part of A is less than or equal to its absolute value. A is exactly equal to positive part of it minus negative part of it. And lastly, the absolute value of A is the summation of its positive part and negative part. Okay. Okay, proposition. absolutely convergent series converge. And moreover, the series AN converts absolutely if and only if the series of the positive part and negative part of the sequence both converge. If the series positive part of ANs and negative part of ANs both converge. In that case we can write the sum of the series is equal to sum of the positive part of terms minus sum of the negative part of the terms. And furthermore, we can have this equality, the absolute summable, the absolutely, absolute value of ANs gives infinite series as the summation of positive part of terms and negative parts of terms. Okay, I guess we can take a break now, right, Professor Fernando? We can take a break if you want. Yeah, yeah, because and then after the break we can continue if it's fine. Okay, thank you for listening to me. Thanks. Yeah. Okay.